Hey, good people. Arthur Morris here. I hope all is well. In this video, we're going to look at extrema on an interval, on a closed interval. So, definition of extrema. Let f be defined on an interval I containing some point c. F of c is the minimum of f on the interval I when the function of c is less than or equal to all of the function of x, the function of x for all of x in the interval. So quick example, if we look down here at the point 0, 1, we have a minimum. You see that's the lowest point on the entire function, and the function is continuous. Uh, then we have f of c is a maximum of f on the interval I when f of c is greater than or equal to f of x for all of x in the interval I. So again, if we look at the same graph here, we see at the point 2, 5 that we have a maximum. That's the highest point on this closed interval that is continuous from endpoint to endpoint. So the minimum and maximum of a function on an interval are the extreme values, or the extrema of the function on the interval. The minimum and maximum of a function on an interval are also called absolute minimum and absolute maximum, or global minimum and global maximum on the interval. Extrema can occur at the interior, like this minimum 0, 1, or it can occur at the endpoints, like the 0.25 there. So extrema that occur at the endpoints are called endpoint extremas. So if we look at this second graph over here, we have a curve uh, that is continuous. However, we have this open circle on each end, which means that it's not a closed interval, so we cannot have extrema at those endpoints if it's not a closed interval. But we do have a minimum here because that's the lowest point on this continuous. 0, 1 is the lowest point on the continuous function there. And you'll notice as we go through some of this that when we find our derivatives and we calculate the derivative at these points of critical numbers, we call them, or inflections right here, that our derivatives will be equal to 0, because remember that the derivative is a line tangent to the point on the curve. And if you see, if we draw a line tangent to the point on this curve, it's a horizontal line which has a slope of 0. Okay, so that should be the case. All right, this third graph, we have this interval is not continuous, so we don't have a minimum down here. However, we do have a maximum because that is the highest point on this function, and it's closed. There, have a closed circle. All right, so finding the value of the derivative at relative extrema. So we want to find the value of the derivative if it exists at the extrema, okay? All right, so we have f of x equals x squared plus 4. So if we want to find the value of the derivative at the point 0, 0, we first need to find the derivative of f of x. So using our quotient rule, low d high minus high d low over low low, x squared plus 4 times the derivative of the numerator, 2x, minus x squared times the derivative of our denominator, which is 2x, all over our denominator squared. Right, and then let's simplify. Okay, so let's see, distributive property here. And then the 2x to the thirds cancel each other out. So f prime of x equals 8x times x squared plus 4 squared. And to find our derivative at the point 0, 0 is what we were asked to do. And again, if we draw a line tangent to that point, that line will be a horizontal line, so our derivative should be 0. So let's find our derivative at 0, 0. So we're going to replace x with 0. And you see we have 0 in our numerator divided by 16, which would be 0. All right. Okay, so that's all we're doing here. We're just finding our derivative at the extremas. The extremum. So we have on number 2, we have the function f of x equals cosine pi of x pi x over 2. And we have extremum, we have a maximum at 0, 1. We have a minimum at 2, negative 1. Okay. So we want to find our derivative of cosine pi over pi x over 2. So first of all, we probably want to rewrite that as f of x equals 1/2 cosine of 1/2 pi times x. Okay, so derivative of cosine of u is negative sine of u prime. So f prime of x should be negative sine of u, and the original u was pi x over 2 times u prime. So derivative of 1/2 pi x. Remember, if we're just looking at this part here, 1/2 and pi are just considered as regular numbers. So we have the exponent of 1, so we multiply 1 times 1/2 pi, subtract 1, so the derivative of that is simply 1/2 pi x, or just pi over 2. Righty, so let's rewrite this. We have negative pi over 2 times sine pi over 2 x, or pi x over 2, however you want to write that, it doesn't matter. And we need to substitute. We have 2 points here, so let's first of all let's look at 0, 1. So when x is 0, we want to know what is the value of our derivative. All right, so we have sine of 0, negative pi over 2 times sine of 0. And sine of 0 is simply 0, so negative pi over 2 times 0 would be 0. Okay, what about when x is equal to, we have the point 2, negative 1, so when x is equal to 2, what is the value of our derivative at that point? So we're still looking at our derivative equation that we have there, replacing x with 2. So we have pi over 2 times 2. So the 2's would cancel out. And then we know sine of pi, if you need to look at your unit circle, you can, but we know sine of pi is 0. And 0 times anything is 0. So again, it proves our point that the derivative at those interior max and mins, maximums and minimums, we call them max and mins, those interior max and mins, the derivative will be 0. Or it possibly could not exist. So another point with derivatives, when we're looking at derivatives, we may have changes like we have here. We have the curve that goes from going down and then goes up if we go as we go left to right, and then in our second graph from left to right we increase and then we decrease, begin to decrease, and then we increase. But sometimes you see that all these curves or changes are smooth curves. Sometimes we'll have a sharp curve like a V. Now, the derivative of a point like that does not exist. So be aware of that. Uh, the derivative of the curves, the changes of the smooth curves, that's where we have the derivative. That's where our derivatives exist. If we have a point like this, then our derivatives does not exist. Okay. All right, so definition of a critical number. Let f be defined at c, and then if f prime of c equals 0, or if it's not differentiable at c, then c is a critical number. Okay. So here we want to find the critical numbers of the functions. So the first thing we need to do is to find the derivative function. Derivative of the function. So we have 3x squared minus 6x using our power rule. And then the second thing we want to do is second step will be to set that equal to 0, because it says if f prime of c equals 0 here. So let's set the derivative equal to 0 and solve. All right, so this is a quadratic, so let's factor. So if I factor out of 3x, it gives me 3x times x plus 2. Set each factor equal to 0 and solve. So that's saying that I have critical numbers or changes in the curve at 0 and 2. So if I were to graph this, and let's see here, let's pause this right quick and just look at the graph. So x third. All right, so let's look at this. I think it was y equals x to the third. Let's see here, x to the third minus 3x squared. So let's look at this one. So x, and then let's raise it to the third. And then minus 3x squared. Sorry about that. Okay, so we said that at the point 0 we had a critical number, which means the curve changes directions, and you see at the point 0 we have that, and then where x equals 2 we have another critical number where the direction of the curve changes. So that's what we're looking at when we're talking about critical numbers, where the curve changes directions. Okay. All right, so back to this problem. Number 13, we have g of t equals t times 4 minus t, and it says t has to be less than 3, because if t were greater than 3, then we would be taking the square root of a negative number. And t can't be equal to 3, and you'll see that in a minute, because we'll end up, once we find our derivative, first derivative, we'll have that radical in our denominator. All right, so let's start over here. So g prime of t, let's first of all rewrite this in exponential form. Okay, and then let's find our derivative. All right, so we have the first times the derivative of the second plus the second times the derivative of the first. We have our product rule with t and 4 minus t to the 1/2. So first t times the derivative of 4 minus t to the 1/2. So we have to use the chain rule in there. So we have 1/2 times 4 minus t times which would, and then subtract 1/2, subtract 1, so that will give us negative 1/2, times the derivative of 4 minus t. And derivative of 4 minus t, you're looking at the derivative of negative t, So that would be negative 1. All right, plus the second times the derivative of the first. So plus 4 minus t to the 1/2 times the derivative of t, and the derivative of t is simply 1. All right, so let's start cleaning this up a little bit. We see we have this negative 1/2 and we have negative 1. So let's move some stuff down to our denominator here. So we have the negative from the negative 1. The t stays in the numerator. And then the 2 from the 1/2 in our denominator, and the 4 minus t in our denominator to change the sign of the exponent to make it positive. And then plus 4 minus t to the 1/2. Alrighty. So I'm going to write this back in radical form now. And let's see here. Let's see if we can go ahead and get this combined into one fraction to clean it up a little bit more. So let's get a common denominator. And I'm sorry I didn't go back widescreen up for us. Let's get a common denominator of 2 times 4 times the square root of 4 minus t. So let's come over here and multiply times 2 times the square root of 4 minus t over 2 times the square root of 4 minus t. All right, so let's see. So now we have the common denominator. So we have negative t, and then plus 2 times, and then the square root of 4 minus t times the square root of 4 minus t is simply 4 minus t. And then in our denominator, we have that common denominator of 2 times the square root of 4 minus t. Then we can simplify the numerator, distributive property, and combine like terms. So if I use my distributive property, that will give me 8 minus 2t, and negative 2t and negative 1t here will give me negative 3t plus 8. Now we should be in a good enough position to find the critical numbers. So let's take this to find the critical numbers. Remember, you need to take your denominator, not your denominator, your derivative, and set it equal to 0. All right, so let's set this derivative equal to 0. And now you see why it says t has to be greater than 3. Because if t is less than 3 or equal, if t is less than 3, should be great. T has to be less than 3, sorry. If t is greater than 3, then we would have a denominator of 0. All right, so let's multiply both sides by 2 times 4 minus the square root of 4 minus t. So multiply both sides by that to clear our denominator. Cancel. That's equals 0. So now we have negative 3t plus 8 equals 0. And then let's subtract 8 and divide by 3. So finally, we see that at 8/3 we have a critical number. All right. So there's a lot of algebra in that problem. As with a lot of the calculus problems we have, there's a lot of algebra involved. So again, to go over what we did, we use our product rule to find our derivative first times the derivative of the second, and within that we had to use the chain rule, and then plus the second times the derivative of the first, and then we cleaned it up a little bit and got it simplified down to negative 3t plus 8 over 2 times the square root of 4 minus t. Then we set that equal to 0 to find our critical number and solve. All right, let's move on. Guidelines for finding extrema on a closed interval. So to find the extrema of a continuous function f on a closed interval from a to b, use the following steps. Step 1, find the critical numbers of f. Step 2, evaluate f at each critical number. Step 3, evaluate f at each endpoint. The least of these values is the minimum, the greatest is the maximum. So you have those 4 steps. Find the critical numbers, evaluate f at the critical numbers, evaluate f at the endpoints, and whatever the least is, that's your minimum. Whatever the greatest is, that's your maximum. So from a graph, you can see it graphically that here we have a minimum at 1, negative 1, and then we have a maximum at 216 on this closed interval. All right, so let's look at this. And now, if you want to pause this and write it down, now would be the time to pause it and write these steps down. Okay. All right, so finding extrema on a closed interval. I want to find the absolute extrema of the function on the closed interval. So step 1, we need to find our derivative because we have to find the critical number. So the derivative of this is negative 1. So we cannot evaluate this anything because we don't have, if we set step 1, it says find your critical number. If we set negative 1 equal to 0 or our derivative equal to 0, that doesn't equal anything. So there are no critical numbers here. And why is that? Well, if you look at that function 3 minus x, we know it's a linear equation, so it's a straight line, so there are no changes in the directions. All right, step 2, it says to evaluate the function at the critical numbers and the endpoints. Well, we only have endpoints here, so we're going to evaluate the function at the endpoints. So f of negative 1, and this is the interval. This is not an ordered pair. Both of these are x values. Okay, so f of negative 1, those are the endpoints. 3 minus negative 1 equals 4. And then f of 2, the other endpoint, 3 minus 2 equals 1. So that tells me where x is equal to negative 1, then I have a maximum. Where x is equal to 2, since the result is 1, which is less than 4, I have a minimum. Absolute max and absolute min. Okay, so number 19. Same thing. First thing you do is find your derivative. So 4x minus 8. And then find your critical numbers. To find your critical numbers, set your derivative equal to 0. And solve. So 4x equals 8. And x equals 2. So I have a critical number at 2. Next step is to evaluate the function at the endpoints and the critical numbers. So let's go ahead and evaluate while we're on step 1 here. Well, we'll just do it all together. So we have 0, 2, and 6. We have 0 and 6 as our endpoints, and 2 is our critical number. We need to evaluate the function at all 3 of those values of x. Okay, so g of 0, looking at the original function. You have 2 times 0 squared minus 8 times 0, which is simply 0. and then g of 2, my critical number there. And you don't have to do it in this order. You just need to make sure you evaluate all three of those numbers. So 2 times 2 squared minus 8 times 2. So 2 squared is 4. 4 times 2 is 8. And then 8 minus 16, negative 8. And then g of 6. So 2 times 6 squared minus 8 times 6. So 6 squared, 36, times 2 is 72, minus 48. So 24. So I have 0, negative 8, and 24. So negative 8 to negative 8 would represent my absolute minimum. That's the lowest value of y result I ended up with, and the highest value was 24. So 624 would represent my absolute maximum. So 2, negative 8 will be my absolute min, and then 624 will be my absolute maximum. Okay. All right, let's look at number 25 here. Let's look at number 25. We have g of t equals t squared over t squared plus 3 on the closed interval from negative 1 to 1. Alrighty. So if we were to, I'd like to look and see if there's any discontinuities, and we have t squared equals t squared plus 3. So if I were to solve that equation for t, I would know that I don't have any discontinuities there. So I'm good. So let's start off. Step 1, let's find our first derivative. I'm going to come over here to the right and find it. So g prime of t. Quotient rule. So the denominator times the derivative of the numerator minus the numerator times the derivative of our denominator all over our denominator squared. All right, let's simplify this numerator. So using our distributive property, we could simplify and then combine like terms. So we have 6t over t squared plus 3 squared. All right, so we have our derivative. So now we should be able to find our critical number or numbers. And remember, we set our derivative equal to 0 to find the critical number or numbers. All right, so we multiply both sides by t squared plus 3 squared. So that would just give us, when we multiply, because we'll be multiplying by 0, so that'll give us 6t equals 0, which gives us a critical number at t equals 0. All right, and then we have the endpoints. Let's not forget our endpoints up here at the top. We have our endpoints of negative 1 and 1. Endpoints of negative 1 and 1. Okay. So we have our critical number. Now we need to evaluate the function, the original function, at the critical number and the endpoints. And the original function is t squared over t squared plus 3. So if I let t equal 0, I get 0 divided by 3, which is 0, or the point 0, 0. If I let t equal -1, which is the first endpoint there, then I get 1 over, what's it, 4. So 1/4. And then if I let t equal the other endpoint, which is +1, still get the same thing, right? All right, so since I have the same y values there, and those are my highest y values, both of these are considered to be maximums. So both of those points will be maximums. And then the 0, 0 would be our minimum, since that had the lowest point. So both -1 and 1/4 and +1 and 1/4 will be a maximum, because the results of 1/4 were the same and they were the highest of the three values. Alrighty, good people, I hope you found this video to be helpful, and I will definitely see you on the next one. Thank you.